Hello and welcome to this new video tutorial of Autodesk Inventor 2018. So this time, instead of 3D modeling, we will be carrying out a very basic FEA simulation. So I have chosen a very simple and static linear simulation of a conrod under tension. So got my engine assembly here. So normally conrods are subject to different types of loading, such as compression, backplane, tension. So normally during the compression and power stroke, there are forces acting on the piston, compressing it, as well as the conrod. So yeah, normally the loads are more even when the conrod is under compression. However, during the exhaust and intake stroke, there is no such loading on the piston. So when the crankshaft is traveling at very high RPMs, the piston needs to change direction very quickly. So that happens in a fraction of a second. Probably we're talking about nanoseconds. So when the piston goes to the top dead center, then the conrod, its mass has to change direction so quickly that it generates really high tensional loads, which sometimes lead to failures. So I have my conrod model here. I've simplified it as much as I can, so I've got rid of unnecessary features, owls, bolts, etc. Simply because those features will just make the simulation unnecessarily complicated. It may also lead to irrelevant results. So okay, if I go on environments now and click on stress analysis, just be aware of the limitations of Autodesk Inventor for FEA analysis, because you have to bear in mind it's linear. It only simulates the elastic behavior of a material. So when a material is stretched beyond the yield point, it will go under plastic deformation. So that will change the cross-sectional area, the results will change. So Inventor is not capable of simulating any of that. So that's why I've decided to just test it against yield tensile strength under static conditions, because it's simple enough for Autodesk Inventor to carry out. So yes, things like compression, which will lead to backplane, the results that Inventor will provide you, I don't believe they will be accurate enough, because under such loading and with the material deformation, the loads will also, the forces will change directions, and Inventor is not able to simulate any of that. So I'll click on Create New Study. It will be a static analysis, single point. So click on OK. Okay, so first thing we have to do, material. It's not completely necessary that you assign a material. The only reason why you would is because Inventor will provide you with the safety, with the factor of safety for that material after you carry out the simulations. Okay. So if we double click on material now, someone carbon steel, you click on materials. So here you can appreciate that I've got carbon steel. This is the library. So normally the first thing that I will do is change the units. So I will click on set display units. and change it. Normally it is already set up on English standard, so I will change it to metric standard. And here you can see several types of steel. So what you can also do, if you find a material that you like, you can always select one of these. You can right click on it, create a duplicate, and then when you double click on it, you should be able to rename it and change the properties for your selected material. So it's just taking a while to load, I don't know why. Double click on it again. Right click on edit, yeah, perfect. So yeah, you can change the description, the name, the appearance, the physical properties. So, as you can see here, this material has a tensile yield strength of 420 megapascal. Yep, that's a fair value. I'll stick to that. Okay, so the next thing to do is apply constrain forces. So we need to apply constraint simply because otherwise our part will be free floating. So when you apply a load, the load will just drag the part away. It is the same as when you use a tensile tester. You first need to attach these specimens. It is the same. I will apply a fixed constraint to this face. I will click on apply. And now we need to apply a load. So if I click on force, I will now select this face. And here where it says use vector components, I will click on it. And then this will allow me to input a force in any direction I want. So I'll input a load of 14 kilonewtons, which is a fair value for conrod, so 40,000 units. And then click on apply. As you can see, in the direction of the arrow, my load is acting in that direction. Okay, so next point, we have already assigned the material, we have assigned a constraint and the load contacts. You don't need to worry about this if you're using a single part. You only apply contacts when you have assemblies, as there will be a contact between different parts. Then the next one to apply will be generating a mesh. So if I click on mesh view, okay, so as you can see, it has split the model into 1067 elements. So you can read here, and 2116 nodes, which are the points that connect different elements. So that's a node, that's another node, that's a node as well. So it's just a very rough and coarse mesh. All we want this for is just to run the simulation to give us a very rough result before we proceed and refine the mesh to get more accurate results. So if I now click on simulate, it will run the simulation. Okay, so Inventor has run the simulation. It didn't take long because we only have 1000 elements. Some FEA simulations may have millions of elements. So yeah, it's not too bad after all. Okay, so these were von Mises stresses. This legend here shows you the different scale for stresses on the model. So it's basically, this doesn't have anything to do with model failure, or it's not necessarily bad. It's just showing you the areas where they are subject to more stress. So it's just a stress map. So you can see that all of that area and this area is taking the least stress, which is around 0.3 megapascals, whereas in this area displayed in red, the stresses are around 200, 230 megapascals. So it is very useful information when it comes to reinforce a part. So if I now go on safety factor, so all of this saying is showing me a map of the different safety factors for my part, and as you can see, these two areas have the maximum safety factor, which is around 15, meaning that the stress would have to be 15 times higher in order to exceed the yield strength of the material that will cause its failure. So it is very, very safe. So you can see that the part is overbuilt in this area, whereas in these areas my minimum yield strength is, my minimum factor of safety is 1.47. So meaning that in all of these areas, I would have to apply 1.47 times the loading in order to cause its failure. You can just have a look at your stresses, and you can simply work it out by dividing your actual yield strength of the material by the stresses in the part. That will give you the factor of safety. So from here I can understand that this is under heavy loading. However, the mesh is really coarse, so we can't really get any valuable information from this. This is only the information contained in one node, as you can appreciate. So we need to refine that in order to get better results. So in order to refine the mesh, what I will do, actually before we proceed with that, I will show you these few functions. So you can animate your simulation. So just click on it, click on play. So that's just showing us how the load is applying to it. It's just to check whether you are carrying out the simulation correctly or not. So it is not simulating the real displacement, simply because the real displacement will probably be under a mil, so it will be hard to appreciate with the eye. It's just exaggerating the range of movement in order for you to be able to visualize it. Okay. You can also appreciate your displacement here. So it's telling you that your maximum displacement is there, and it's 0.1 of a mil. So again, that's the reason why in the animation it's more exaggerated. Another thing you can do, you can add probes. So just click on probe, and then you add a probe anywhere, and will tell you the stress at that point. So let's proceed with the mesh refinement. So if I click on local mesh control, I can now select faces or edges. So I'm going to select these two faces, and I'm going to make them 0.9 of a mil. This will determine the element size in those faces. So here in your mesh settings, you can see your global mesh settings. So as you can read, your average element size is 0.1 and your minimum is 0.2. So now when I click a right click here to update the mesh, it will take longer to compute because it will require a larger number of elements. So if I zoom in now, as you can see, it has increased the number of elements greatly. So now, if I now click on simulate and I click on run, so as you can see here, my results have changed a lot simply because I have a larger number of nodes. I am now getting better information about the stress. So as you can see here, the higher stresses are where in this corner where these two faces join, simply because stresses tend to concentrate in sharp corners, and you can see the same here. So as you can see, the information has already become a little bit more accurate. And again, you can always refine it farther and farther to get better results. Okay, so as we can see here, our maximum stress is 276, and our safety factor right now, our minimum safety factor is on 1.26. So we need to fix that somehow, simply because an extra 25% is 26% is not enough to make the part reliable. So if I now go on my parameters, or in your case, if you haven't set your parameters, you can always finish your analysis, go back to your model, edit your model, and then go back to the analysis, and you will just have to update it. So right now, my thickness, so between this wall and this wall, is currently on 1 mil, which is clearly way too thin. So if I make it maybe 5 mil, just enter. So now the model should update. And also another thing that I will do is I will fillet these edges in order to minimize stress concentration. So stress will distribute more evenly around the fillet. So that should also improve the integrity of the part. So if I now go back to my environment, stress analysis, so now I have to update my mesh. Okay, so simulation has finally solved. So after those two modifications, my maximum stress has gone on 140 megapascals, and my minimum factor of safety is on 2.5, which is more than reasonable, meaning that I could probably reduce the amount of material in my model to make it lighter. So yeah, an FEA simulation is basically about constantly refining your mesh, adding small features such as fillets or chamfers into your corners in order to prevent stress concentration, and yeah, and every time you do these little refinements, your results should become more accurate. So it's just an iterative process. It's just repeating and repeating these steps over and over again until you get there. So this is for today. Thank you very much for watching, and I will see you in the next one.